Okay, so, right, we just saw that factorials dominate exponentials. And so now we looked at proving two limits, right? We generalized how to show that, like, the limit of that nice expression went to e to the x. We also looked at the limit of, like, a factorial over an exponential and vice versa. So now what I want to do is I'm going to show you the 6 most commonly occurring limits that are in your textbook. We've proved a couple of these already. Some of them are pretty intuitive. So if you see any of the limits I'm about to show you, or you recognize them, you're allowed to just cite them, okay? You don't have to prove using L'Hopital. We don't have to do any major background work. So, excuse me. So, these are commonly occurring limits. More specifically, the expressions that live inside these limits are going to be converging sequences. So if we ask you if something converges, right, and you recognize one of these 6 things, we just know that it does, and you can cite it, and we can prove it using the infinite limit test and citing it out, okay? So the first one is that the limit as n goes to infinity, of the natural log of n over n equals 0. So since this limit goes to 0, if you look at this, right, well, the natural log of n is going to go to infinity as n goes to infinity, because it's an increasing function. But if you remember what logs look like, they're the inverse of exponentials. So even though they increase to infinity, they sort of bend, and so as n gets bigger, it's increasing at a decreasing rate, right? It levels off. 1 over n, however, or n, excuse me, in the denominator is going to infinity, but n is just sort of like the line y equals x. So what we're actually saying here with this limit is that n, like, is going to grow faster to infinity than ln is going to go to infinity, and that's why the whole limit's going to end up being 0. Okay? So the denominator is outpacing the numerator here, right? So the second one, which we're going to use a lot later when we get into series, you'll see this guy crop back up, is that the limit of the nth root of n goes to 1, right? So another way of seeing this written is, remember, we can rewrite radicals with fractional exponents, and I can say that's the same exact thing as just saying the limit as n raised to the 1 over n goes to 1. Clearly, if we wanted to prove this guy, because we have a variable raised to a variable, we'd have to do that natural log trick again, like we did with the e expression, right? The third one says the limit as n goes to infinity of x to the 1 over n equals 1, as long as x is greater than 0. So remember, in these, it's a little, we mentioned this before, right? It's a little weird to see these x's and n's mixed together. These x's represent constants. So when you see this, nobody's just going to give you x to the 1 over n. It could be like 2 to the 1 over n, right? 3 to the 1 over n. So the x is going to represent a real number, and as long as it's greater than 0, we know it'll the limit will be 1, right? The fourth one says the limit as n goes to infinity of x to the n is 0 as long as the absolute value of x is less than 1. So in this, what we're really saying in this expression is that x represents a fraction, right? And so what we mean by the absolute value is it could be positive or negative. So I could have negative 1/2 to the n. That limit would go to 0, right? I could have positive 1/2 to the n. That limit would go to 0. But hopefully, for obvious reasons, if x gets greater than 1, right, we know that thing's going to blow up to infinity. So like 2 to the n, right, is going to blow up to infinity. 3 to the n is going to blow up to infinity. So it's got to be a number less than 1, or this isn't gonna work. All right. 5 is our old friend that we've already proved. And we've already established that this is going to be true for any x, positive or negative. And then we just saw when we compared factorials to exponentials that a factorial, right, dominates an exponential. So as long as the factorial is in the denominator, right, this limit will be 0. And this is also true for any value of x. All right, so let's look at a couple quick examples, working with a few of these, kind of showing how you can just kind of cite them outright. And then we'll talk about a couple other quick little useful theorems, okay? So when we finish this section, right, we'll have a quiz next week. I don't want to do it on Monday because that's our short day, so we're going to do it on Tuesday, but it will be over 9-1, and I'll post it, if I can remember. I'll have it up before the weekend's out, so you guys can start looking over it, but it will be all over all of 9.1, and then we'll just start 9.2 on Monday. All right, so let's look at a couple quick examples, and then I'll show you 2 more fun little theorems. So let's look at 1 plus 3 over n to the n. Oops, should be curly bracket. So we still need to apply the limit test, right? I still want to see you at least get me to there, right? So you understand that the only way to test for convergence is to apply the infinite limit test. However, I can be like, well, I recognize that limit, right? And the x value in this limit would be 3. So this is e to the x, which in this case is e cubed. So now I can say a sub n converges to e cubed. Now with this limit, if you flip a limit, right, the ratio of the limit, you should flip the answer, okay? So one thing I want to point out about this guy is you'll see it a lot, but you may not always recognize it. So you want to make sure that you understand what it looks like. So if I were to write 1 over 1 plus 3 over n to the n, and take the limit of that, well, this would just be 1 over e cubed, right? That's pretty straightforward. If you saw it like that, most of you could probably get there, okay? But if I do a little bit of algebra, right, when you flip a limit, or when you flip a fraction, right, we multiply times the reciprocal. So let's just look at a little bit of algebra here just to kind of give you an idea of what else this could look like. So if I have 1 over 1 plus 3 over n to the n, and I didn't want to write it like that because that's big, ugly, and gross and takes up a lot of paper, okay? So I'd say, well, let's condense this down. So the first thing I might do is I'm like, well, let's get a common denominator in here so we can simplify this. So if I get a common denominator, that common denominator is going to be n. So I'm just going to multiply this first term by n over n, right? And now it would look like that. And then when I flipped it, because I multiplied times the reciprocal, it would now look like this. So if you see the limit as n goes to infinity of n over n plus x raised to the n, that is equivalent to 1 over e to the x, and that's still true for any x. So you guys see the difference? So a lot of people, they see that in a problem and they don't actually recognize that that's a form of e. So if you undo those algebra steps, you can get right back to this spot and see that, oh, it is in fact just 1 over e. So when you're looking at limit number 5, I might make a little star by it and realize that's another commonly occurring form of that same limit. Does that make sense? Okay, and once again, that x is going to be represented by a number. All right, cool. Any questions? No? All right. Like, you promised we could leave early. Just get it done, right? Okay, so this is a very, very useful idea. And we're going to use this a lot when we have alternating terms, right? So when we have things that are bouncing back and forth between positive and negative numbers, right? We're adding a little bit, then we take a little away, then we add a little bit, then we take a little away. So it can be kind of hard sometimes to see what those types of sequences converge to, because they look like they're bouncing back and forth between two values, even though they are settling on something. So if any of you ever took physics, right? And even if you didn't, this is an easy concept to understand. So if you have a sine or a cosine wave, right? In theory, it just goes back and forth between -1 and 1 forever. And if you look at a spring, right? If you pull a spring and you let that spring bounce up and down, well, in theory, if the spring is perfect and ideal and we didn't have gravity and other things to deal with, that spring should just bounce forever, right? If there's nothing slowing it down. But in reality, we know that if you pull a spring and you let it bounce, eventually it stops, okay? Well, if you map that motion, it actually looks like a wave. It's going up, down, up, down, up, down. So we actually call that the thing that makes it stop, we actually call it damping, okay? So what that would look like if I had a spring is you'd see a wave, and then you would see the amplitude just decreases, 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 right? But you can still see that those amplitudes are approaching zero, right? But if I let this dotted line right here be the relaxed length of my spring, which would be x equals 0, we can see we get a positive number, then a negative number, then a positive, then a negative. So with these alternating series, when they converge, you see a positive value, then a negative value, then a positive value, then a negative value. But if it is converging to some value, right, and you graph the dots of the function, it would look like this. You would just see dot, 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 and then it would start settling on some number. And that can be a little hard to detect, especially if those fractions take a really funky looking form, okay? And not everybody can do those in their head. So what the absolute value theorem says, that if you take the limit of the absolute value of the nth term, so we can already kind of imagine in our mind, if we've got a -1 raised to some stuff and I take the absolute value, well, that -1 term just becomes 1, right? Because it's just the absolute value of 1 is 1, the absolute value of -1 is 1. So basically what this theorem lets us do is it lets us get rid of that, look at the remaining part of the term, and if this converges to 0, then we can say the original term converges to 0. So let's look at an example. So I'm going to let a to the n be -1 to the n over 2 to the n. Now, we know this converges, and I've told you guys, we're going to look at this guy a lot, you hear me? So you better know, if any of you can't tell me 1 over 2 to the n or -1 over 2 to the n converges by the end of this class, I have failed you miserably, because we're going to look at this from a million different ways. All right, so we know the limit of this is 0, right? We know, because it's a constant. We actually used the squeeze theorem and looked at it, right? We can squeeze it between -1 over 2 to the n, 1 over 2 to the n. But another way we can look at this, we can just apply the absolute value theorem, right? So the absolute value of a sub n, right, is just the absolute value of 1 to the n over 2 to the n. And that's just going to equal 1 over 2 to the n. Because the numerator will only ever be 1 or -1. And the absolute value of both of those numbers is just 1. Okay? So if I can show that the limit of all the positive terms converge, then surely, right, the negative ones will as well. Okay? So if you were to actually graph this, like if we looked at the positive case, we know this is 1/2, 1/4, 1/8, 1/16. But what this sequence is saying is, well, it's -1/2, positive 1/4, -1/8, positive 1/16, okay? So if I were to graph those, you would see that those fractions get smaller, 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 right? They just bounce up and down as they do it. So now I'm just going to take the limit of the absolute value right? Which hopefully we all know now is 0. So, by the absolute value theorem, the limit of this is also 0. So this gets around the squeeze theorem. So there is no one direct right way to prove that 1 over 2 to the n converges, right? You're going to actually have probably about 10 different ways to show me that by the end of the unit. And the idea here is to keep showing you how many different ways you can arrive at the same answer. As long as your method is valid and you justify what you're doing, I'm okay with it, okay? All right. So the last thing I want to talk about today are monotonic and bounded sequences. Oh, sorry, question, what's up? Because the numerator will only ever be 1 or -1, right? So the tell of when you want to use this guy is going to be when you see a -1 raised to some stuff, right? Because what the absolute value is, it just removes that part of the term out, and we look at everything else, and we know if it absolutely converges, then the alternating sequence will converge, okay? So the last thing I want to show you about how to test for convergence, right, is we're going to look at something called monotonic and boundedness, okay? So what is a monotonic sequence? So mono means 1, okay? So a sequence is monotonic if its terms are non-decreasing. So what we mean by that is mono means 1, so literally we mean the sequence is moving in one direction, right? And not the band. One direction, okay? So that means it's steadily increasing or it's steadily decreasing, right? So non-decreasing means increasing. That's a really lame way to define it, but that's how it's usually defined, all right? Or the other way are if its terms are non-increasing. So it's just getting smaller. So that's what we mean when we say a sequence is monotonic, right? It means everything's either steadily increasing or steadily decreasing. So that alternating sequence we just looked at, -1 over 2 to the n, would not be monotonic. 1 over the 2 to the n positively would be monotonic, right? It'd be monotonic decreasing because every term would be smaller than the previous term. So sometimes, for monotonic sequences, they can be really obvious. You can just look at them and tell whether they're increasing or decreasing or not, or neither, right? 1 over 2 to the n, another great example, right? Steadily decreasing. But sometimes you just can't tell, okay? So I'm going to show you one where we can obviously see what's going on, and then I'm going to show you one that we just can't quite tell, and there's a method you can do to test to see if it's monotonic or not. So the first one is our old friend, 3 plus -1 to the n, right? And we know that this guy diverges, right? It just bounces back and forth between 2 and 4. And so clearly, this is not monotonic, right? Because it goes from 2 up to 4, then back down to 2, then back up to 4. So it's not moving in one direction. It's bouncing up and down. This one, however, well, I can't quite tell. I mean, the numerator's multiplied by 2n, the denominator's 1 plus n. It's a little more complicated, right? And for monotonic, it's got to be from step 1 dropping, right? Or from step 1 increasing. So we don't know what's really happening. So what you can do is we can generalize any two arbitrary terms and see what's happening. So what I want to know here is how does the nth term compare to the nth plus 1 term? So that little box I've drawn is what I want to set up as an inequality. I want to know, is it greater than or equal to or less than or equal to, but I don't know, okay? What I do know is that I can algebraically work with an inequality just like I would an equal sign, and as long as I don't multiply or divide by a negative number, that sign stays intact. So what you can do here is we can actually set up the algebra until we get a well-defined expression that we can determine, and then we can backfill the sign in. So here's what we do. We take the nth term, which is 2n over 1 plus n, and we're going to compare it to the n plus 1 term. So you just plug n plus 1 everywhere you had it in. This denominator here is going to be n plus 2. Does everybody see that? Because you're just going to say n plus 1 plus 1. So what I'm going to do, since all of these values are positive, I know I can cross multiply without violating my expression. So I'm going to say, well, I have 2 to the n times n plus 2, and I want to see how that compares to 2 to the n times n plus 1 squared. So this was 1 plus n, that's the same thing as saying n plus 1, so all I did was cross multiply these two terms. Then I want to expand each side out. So on the left side, I'm going to get 2n squared plus 4n, and I want to see how that compares to 2n squared plus 4n plus 2. So I FOILed out n plus 1, and then I multiplied every term by 2. You guys should be able to handle that by now. All right? Now let's compare these guys. Well, I have a 2 to the n squared and a 2 to the n squared, so I can subtract that from both sides. I have a 4n and a 4n. I can subtract that from both sides. So basically now what I have is 0 on the left and 2 on the right. That's a very clear picture of what's going on. So I think we're all cool with the fact that 0 is less than or equal to 2. And since I didn't do anything that would have required me to flip the sign, I can backfill and I can see that a sub n plus 1 will be bigger than a sub n, and this sequence is monotonic increasing.
How'd you get from the second step to the first?
From here to here, I cross multiplied. So 2n times n plus 2, and then 1 plus n times 1 plus n. Yep. All right. So why the hell do we care about this? What is it going to do for us? All right. So if you know that a sequence is monotonic and it has one additional characteristic, we automatically know it converges. All right. So if you recognize these two things, I'm going to show you the second caveat in a second, but when you recognize those two things in a sequence, you can cite this theorem and you're done. You don't actually have to show any work, right? Other than maybe proving to me that it's monotonic by listing out the terms, or maybe doing the inequality. but it's a really nice thing to do. So just remember, sometimes the limit stuff just isn't possible, so you got to get creative when you're trying to prove whether something converges. So, oops. So we've looked at whether a sequence is monotonic, but now let's talk about what bounded means, okay? And this is going to be one of those things, a lot of words to describe something simple, but you need them in case you need to reference it, all right? So a sequence is bounded above if there is a real number, we'll call it capital M, such that A sub M, or A sub N, excuse me, is less than or equal to M for all N. And M is called the upper bound. So if a sequence is monotonically decreasing, right, meaning its first term is its biggest term, and then it decreases, 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 decreases. Well, then by default, you've got your M. You know it's bounded above by that first term, right? It's never going to be bigger than that. It's just going to decrease from there, okay? A sequence oops. God, guys, struggling. All right. Is bounded below if there is a real number, we'll call it capital N, such that A sub N is greater than or equal to N for all N. And N would be the lower bound. So we actually used this idea on Tuesday when we talked about the squeeze theorem, and I gave you 1 over 2 to the n, and what was the number we said that 1 over 2 to the n always had to be greater than? 0. So if you know all the terms in your sequence are positive, they automatically have a lower bound, and that lower bound is going to be 0 by default, right? There may even be one bigger than 0 that works, but you know if all your terms are positive, it's bounded below, okay, by 0. So a monotonically increasing sequence, right, is bounded below by its first term because the first term is the lowest one, and they get bigger and bigger and bigger from there, right? So this is only when we talk about, so basically we're saying this sequence has a ceiling, this sequence has a floor, okay? But we call a sequence bounded, right, without the above or below, if it's bounded above and below. So can anybody think of a sequence that we've seen a lot that we know is bounded above and below? Sine, right? Bounded by 1 and -1. What's the other one that we've written out about 20 million times? Very first one I ever showed you. That 3 plus -1 in the end, right? That bounces between 2 and 4. It's bounded below by 2 It's bounded above by 4, right? And so notice we can say 2 and 4 are the bounds because we allow for it to be less than or equal to that value. So we can say that. So a sub n equals 3 plus negative 1 to the n is in fact bounded. N would be 2 and m would be 4. So we've talked about things being monotonic, and now we've defined what boundedness means. So what happens if something is both? So this example we just looked at, right? This guy's bounded, but it's not monotonic, right? So a bounded monotonic sequence is really awesome because if you can identify that a sequence is bounded and monotonic, then it converges. Sorry, I lost a page in my notes, guys. Hold on. All right, so let's look at an example. A sub n is equal to 1 over n. So we know that this guy is bounded below by 0, right? Because all these terms will be positive. So definitely got a lower bound, right? What about the upper bound? Do we have an upper bound? Well, 1. Is it monotonic? Right? So those of you that said it's bounded by 1, you're right, because the first term is 1, right? And we can kind of sort of see that all these fractions are going to get smaller and smaller and smaller, right? But we need to show, is it monotonic, all right? So what does a to the n look like compared to a to the n plus 1? So we get 1 over n, 1 over n plus 1. Once again, I'm just going to cross multiply. And clearly, I think we're good here, right? We don't have to go down to 1, 0. Clearly, this thing on the left is greater than the thing on the right. So I kind of could see that already, that this is going to be monotonically decreasing, right? 1/2, 1/3, 1/4, 1/5. If you kind of list out the terms of the sequence, they are getting smaller and smaller and smaller. So if it's monotonic and decreasing, and it's bounded, then it converges. We can also see that it converges because we could apply the nth limit test, right? And the limit of 1 over n is 0, so we know it converges to 0. So we can confirm that this theorem is telling us the truth because we had another way of verifying that the sequence converges, right? Does anybody not see the bounds? It's important, so like speak up. Yeah.
So the capital N equals 0, like the way we got that was we just thought like that N equals like infinity and then 0.
No, the reason I got n equals 0 is because I said, well, those terms are always going to be positive, right? For every value n you pick, 1 over n is always a positive number. So therefore, it's bounded below by 0. Those terms will never go below 0, ever. Huh?
Why wouldn't it be like a negative?
Well, because if you can identify that, so when we write an inequality that's greater than 0 or less than 0, what we're really defining is it's positive or negative, right? So if I say x is greater than 0, what I'm actually telling you is x is a positive number. If I say x is less than 0, I'm telling you x is a negative number. So there may be other bounds that work, but if you know terms are always positive, you can at least say they're bounded by 0. All you have to do is find a bound. It doesn't have to be the closest bound, right? But since this sequence converges to 0, right, that means all the terms are approaching 0. They're never going to quite get there, but they're going to approach 0. So therefore, 0 would be probably the best lower bound to pick in this case. And then the upper bound, well, the very first term is 1, right? And then they decrease from there. So these terms are never going to be bigger than 1, and they're never going to be below 0, so we know we're bounded by 1 and 0. Yep.
So I know that it's tells us that it converges, but how do you find out what it converges to?
Well, for a sequence, whatever the result of the limit is what it converges to. So in addition, this thing converges to 0. And so I picked this one as the first example because we have an alternative method we're all comfortable with to show convergence, so we can verify this theorem does in fact hold up. Okay? All right, so let's look at another one that's a little trickier. So I actually know from looking at this from the nth limit test that this thing's going to diverge because the limit's going to be infinity, okay? But let's show how this theorem will also get us to that same result, right? So the first thing I need to know is this thing monotonic, all right? So we can check that it's monotonic, right, by comparing the nth term to the nth plus 1 term. Once again, I'm going to cross multiply my terms. So I've got n squared times n plus 2. And I'm going to compare that to n plus 1 cubed. Okay? So all I did was cross multiply. When I expand this out on the left, I get n cubed plus 2n squared. On the right, when you expand this out, we get this. So I can already see that the right side, and you do this algebra till you get to a line where you're comfortable going, oh, this side's clearly bigger than this side. As soon as you've identified that, you don't have to keep going. But the stuff on the right, this is going to be bigger than the stuff on the left. So this sequence is monotonic. It's monotonic increasing, right? And the reason I'm allowed to state that it's monotonic is because this inequality, the way we're setting it up, tests for any arbitrary n term and compares it to the next term in the sequence. So we're generalizing this test. However, is this guy bounded, right? Well, it's definitely bounded below by 0. These terms are all going to be positive, but does it have an upper bound? And the answer is no, because we know the limit's going to go to infinity. So it's monotonic, but not bounded above, so we know that it diverges. All right, and then I can confirm that as well with the nth limit test, okay? So let's just look at this alternating series. Just -1, 1, -1, 1, -1, 1 forever. Okay. This guy's bounded, right? It's bounded below by -1. It's bounded above by 1, but it is not monotonic, so it diverges. So this is a great example of one. If I said, does this series converge or diverge? If you understand this concept, boom, you're done. So if you state something's bounded, you better give me bounds. And there could be more than one correct answer for the bounds, but this thing will never go above 2 or below -2 either. Those are technically, I mean, you know, it's, you just got to find a bound and then tell me whether it's monotonic or not. Yep.
So if it's bounded and monotonic, like if and only if it's bounded and monotonic, then it converges.
Yep, and it's got to be bounded, meaning you've got to have an upper bound, a lower bound, and it's got to be moving in one direction. It could be monotonically increasing, it could be monotonically decreasing, but as long as you can show, right? Conversely, where this theorem really is helpful is showing something diverges. Because it's really easy sometimes to show something's not bounded, and it's really easy sometimes to show something's not monotonic. So if both of those things are not true together, this thing can't converge. And so this is a great example of a sequence where this theorem would come in really handy. Okay? All right, so last thing we're going to talk about today, very quick. This is actually supposed to be fun. I always save it to the end of the section because you're going to be doing this in 9-2 a little bit, and I want to make sure we've just played around for a second. So we're just going to do one or two little quick examples. So I told you guys back at the beginning that when we look at sequences, a sequence is a list of numbers, right, that are ordered, and they have a discernible pattern. So up until now, I've been giving you the pattern. I've been giving you an equation or expression, and then from that you plug in your ends and you get the list, right? What do you do if I give you the list and I need you to write back what the pattern is? So the reason I always like to push this to the end of the section is now that we've seen lots and lots of different sequences and we've kind of seen the elements that live within those sequences and what they kind of do to the numbers, it's a little easier for you now to put those components together. So let's look at a list of numbers and we'll see if we can find the pattern. And these are fun for me because it's just puzzles. Puzzles and games. Okay, so first sequence, -2/1. The next term is 8/2, -26/6. And you're also going to see here why, when we generate a lot of these sequences, we do not simplify the fractions. Because if you simplify the fractions, you kind of lose the pattern, right? And we want to make sure we keep them where they are. So, does anybody see, in anything you recognize, what's the first thing you notice that's maybe happening to this guy? Okay, I heard two things. So you got alternating, what was yours? Got it, okay. So she saw it's alternating back and forth between positive and negative, and he recognized the denominator is in factorial. Both correct. All right, so, sorry. So let's deal with both of those. All right. So if it's alternating, right, that means we got -1 raised to some stuff, right? Because that's what's going to make it bounce back and forth, positive or negative. So now we got to figure out what's put in that exponent, right? And he was correct about in factorial, so we'll just go ahead and throw that in the denominator because that's easy. That's just a straightforward one, okay? So if we start from n equals 1, which we kind of say we default to if it doesn't tell us we can start from 0. If we start from n equals 1, then I need the first term to be negative. So if I just pop an n in the exponent, well, -1 to the 1 will in fact give me the first term negative. Then when I square it, the second term's positive, right? So that'll work out just fine. So this -1 to the n is going to make everything alternate. So the numbers in the numerator are a little tricky. The first two look like powers of 2. The first two look like powers of 2, but then 26 is clearly nowhere near a power of 2. What if you were to add 1 to every number in that numerator? Somebody see a pattern there? Powers of 3. So 2 plus 1 is 3. 8 plus 1 is 9. 26 plus 1 is 27. So what these are is these are powers of 3, and then you've subtracted 1 away. So, excuse me. Now if we plug in values, right? When you plug in 1, you get 3 minus 1 is 2. When you plug in 2, you get 3 squared, which is 9 minus 1 is 8, right? Then you get 27 minus 1 is 1, right? Let's look at one more. That's it. If we want to know if this sequence converges, well, I want to do the nth limit, but since I have that alternating term, we should try the absolute value theorem, right? So if the absolute value of this stuff converges, then we know the original sequence converges. So all the absolute value does for me is takes away the -1. So does anybody recognize this limit? What's going to be? 0. You have an exponential in the numerator and a factorial in the denominator, and we said that factorials dominate exponentials. So this guy's 0. So now we can say a sub n converges to 0. All right, let's look at one more. So the idea here too is if you can do it this way, if you can generate the a sub n from the list of numbers, then now when you're looking at those a sub n terms, you can recognize certain things and you know what those numbers are going to do, okay? So when you see a -1, you know they're going to alternate, right? So what do we see happening in the numerator? Huh? Sorry, air conditioner, I can't hear. What? Right, it's doubling every time, okay? So when something's doubling every time, that's probably an exponential, right? It's probably 2 to the n. So 2 to the 1 is 2, 2 squared is 4, right? 2 cubed is 8. So the numerator is 2 to the n. What's happening in the denominator? Huh? It's +2, but more specifically, it's all the odd numbers. Okay? So how do you write a number that's odd, right? Well, we need the first number to be 1. So there's 2 ways we generalize an odd number. For even numbers, right, we say, well, it's 2 times some number, some integer, right? But for odd numbers, we kind of, I mean, there's more than one way to do this, but for odd numbers, these are kind of with a baseline where we usually start. So we could say take an even number and add 1 to it, or we could say take an even number and subtract 1 to it. So which one do I need in my denominator? Because I want to plug in n equals 1 in the first term. The subtract one, right? So this is going to be 2n minus 1 in the denominator. If we look at the limit of this, we have an exponential on the top and a line on the bottom, right? So we can kind of see this is going to blow up to infinity. So this sequence diverges. All right, so this is the end of section 9.1.